Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. The series is Individual and Social Choice. This is installment 8 in the series, and in this installment we're going to think about voting rules in an axiomatic kind of general way. What I hope to get to is a famous result called Arrow's Impossibility Theorem. Okay, this is a theorem proved by Kenneth Arrow. It was published in a book called Social Choice and Individual Values. The second edition, which corrects an error, is 1963, but he had the result done in the 50s. So, and it represents, in terms of the literature, a really innovative and big step forward from looking at properties of specific voting rules to taking a general perspective and saying, well, what are we looking for? What are the properties we want a voting rule to satisfy? And then, given those properties, kind of work backwards to see what rules satisfy them. He's not the first person to do axiomatic work, and there are well-known axiomatizations for certain voting rules. But Arrow kind of looks at these key properties, and which we'll describe next. And unfortunately, as the name sort of suggests, it's the impossibility theorem. The outcome of that is that we can't find a satisfactory voting rule, at least in the sense of satisfying these axioms. So it's really a mathematically beautiful result. It's at the core of social choice theory, formal political theory, and it's fun to start thinking about. There are some kind of counterintuitive things that we'll run into, but let's just move ahead. Last time we talked about properties of majority voting and Borda, and we talked about them without actually defining them in a formal way. In fact, we don't really have a way of doing that yet. So what I need to do is put more structure on the model, and so we'll have to enrich the model to start thinking about voting rules in a way that's systematic and general. Okay, so as a first step, think about majority voting. What did we do? We said, well, given any preference profile, here is a rule for calculating this majority preference binary relation. Okay. Now, because that rule was stated in a general way, it didn't matter which preference profile you started with. The same rule would give you the majority preference relation for any one of them. So what I want to do is think about that as a mapping. Okay. Now, I should say, so just a little mathematical aside, the terms function and mapping, I'm going to use those synonymously. They mean the same thing. We've seen functions before, obviously. We've graphed functions from that take real numbers and give you back new real numbers, right? We also actually, we were talking about utility functions, and we talked about a utility function or representation as assigning a number to each alternative, and even if those alternatives weren't real numbers, we could still plot the utilities of those alternatives. So in that case, x was just some finite set. That was the domain of the function. Okay. Well, really, you can think about functions in super general ways. All you really need is a set, well, two sets. One is called the domain, and the other is called the range, or range space sometimes people might say. Right, so there's some set called the domain. There's some things in it. Maybe it's the real line. It could be infinite, it could be finite, it doesn't matter. It doesn't matter what they are. And same with the range. And what a function or a mapping does is to each element of the domain, it assigns some element in the range. It's just an assignment. Okay. It can assign the same thing to two different elements. Here's two elements that are assigned the same thing in the range. The only thing it can't do is assign two things to one element. We can't have something like this because now, oh, this element here is being assigned to do two different things. So we're not going to allow that. We do have to, assign something to each element, and yeah, there's a lot of arrows flying around here. I'm just going to get rid of that guy. All right, so this is a function. Each element in the domain has been assigned an element of the range. Some of them are assigned the same thing, and there's actually some elements in the range that are not assigned to anything, and that's fine. Okay. Now, the reason I'm talking about this is because I want to think about a function that assigns to each preference profile a binary relation that represents some, I'll call it a social preference, okay? And so let's let, we'll have our domain be all possible preference profiles. And the range will be, let's say, asymmetric relations. In other words, those are like P's, right? Those are our strict preference relations. Now, these sets are, they're pretty big. Even if there's only a few alternatives, the number of preference profiles gets big pretty quickly. If there's a lot of alternatives and a lot of people, this can be a huge set. And actually, there can be an infinite set of alternatives. But majority voting, then, is taking each preference profile to some social preference, okay? It's doing what our definition was doing, okay? Now, this is so we can define this majority preference function. We actually did that, but we just didn't have the language for it. So we've defined a majority preference function, and let me give some notation for it. I'll use a little f for function and subscript m, so we know it's the majority preference relation. So then this function takes a preference profile as an argument, and then gives us a binary relation. Okay, this is like our PM. Okay, I'm just using this kind of functional notation so we can see how it really depends on the preference profile. All right, and then it's defined just how we always did, how we defined it before. So we define this majority preference function so that x beats y if and only if the number of people who prefer x for this profile is bigger than the number of people who prefer y for this profile. You can see how, you know, this inequality here depends on the preferences of these individuals, and that's reflected in the argument of this majority preference function. Okay. So this is our formal definition of the majority preference function. In fact, let me just make that definite here. The majority preference function is defined as follows for all two alternatives for any x and y. X beats y if and only if more people prefer x than prefer y. Right? So this is the majority preference function. It's this definition we already saw. There's not really anything new here. We're just thinking about it in a different way. We can think about this as a function. Same with Borda. We can think of the Borda preference function and I would just use a subscript b, but it would be defined the same way. The same way as we defined Borda before. So I'm not going to really write all this out because it's kind of a, takes a while to define, all the Borda scores from each individual and the total Borda scores, but we could do that. Right? And then we would use the same kind of notation. So this Borda preference function, if you plug in a preference profile, it's going to give you a binary relation that says x beats y if and only if it has a higher Borda score. And I'm not going to write all that in because we've already defined that stuff. Okay, it's just a different way of thinking about this Borda voting rule. We can think of it as a function that depends on the preference profile. Okay, but now those are just two specific voting rules. There's lots of other voting rules, ones we haven't talked about explicitly. There are voting rules people haven't even imagined yet. There's a ton of them out there. So without talking about a specific one, I can just say, well, I can refer to a mapping from preference profiles to social preferences. Okay, I'm going to call that a social preference function. And what is it? It's a function. Let's call it little f with domain equal to the set of preference profiles and range equal to the set of asymmetric binary relations on the set of alternatives. Okay? It's just what we drew above, right? When we were talking about majority rule, we had a domain of preference profiles and a domain of asymmetric range of asymmetric binary relations, and a social preference function just assigns a social preference to each preference profile. Okay. Well, now we actually have the ability to go back and talk about properties of voting rules in a formal way. Okay. When we were talking about majority voting in Borda, we talked about a couple of these in an informal way. Right, so here we're talking about properties of voting rules in general. We're thinking about that now as a social preference function. Right, and one of the properties we talked about was the possibility that a voting rule could always generate a ranking, and we saw that Borda possessed that property because the preferences were based on points. Majority voting did not satisfy that generally. But now I can define that property in a formal way. I'm going to call it rationality. What does it mean for a social preference function to have this property? Well, it would mean that for all preference profiles, that the social preference function is asymmetric. Well, I'm building that into the range, okay? So the key property, though, is that it's negatively transitive. Let me just write that out. It's asymmetric and negatively transitive. I'm kind of building asymmetry into the idea of a social preference function because the range only consists of asymmetric relations. The key property is this negative transitivity. Okay. The Borda social preference function, the Borda preference function has this property. Majority rule does not, because there are some profiles where majority voting does not give you a ranking. Okay. Now, the other property that we talked about was the idea that to figure out if one alternative beats another, you could just have individuals raise their hands and say how many people prefer X and how many prefer Y. We saw majority voting has that property. That's pretty clear. But Borda does not if there's more than two alternatives. Okay. We can actually formalize that in this framework, and this is Arrow's contribution. He defined this property as independence of irrelevant alternatives and just so I don't have to say that and write it out again, we'll call that IIA. All right, and now this is a little bit different, and the way of formalizing this might be counterintuitive, but what we're really saying is that, well, let me just write it out and then we can talk about it. So, so the property is for all profiles P1 to Pn and P1 prime to Pn prime. Okay, so notice I'm now considering two different preference profiles here. Okay, for any two preference profiles, and for all pairs of alternatives, x and y, suppose we take a pairwise vote between x and y, and we ask how many people prefer x in the first profile. So in that first profile, the people who prefer x it's this set here. It's the set of people who prefer x to y, the set of people who prefer y to x is this. Suppose those are the same in each, in the two different profiles. Okay, so the set of people who prefer x to y in the second profile, it's defined the same, but I'm going to use this pi prime. Okay, this little apostrophe thing, I'm going to call that a prime. I'm just using that to distinguish the second profile from the first. So the set of people who prefer x to y, given the second profile, I would write like so. The set of people who prefer y to x under the second profile, again, it's similar, but I'm using a prime here, okay? So suppose that we have these two profiles, we have these two alternatives, we take pairwise vote between x and y, and the outcome of the vote is the same in the two profiles, okay? So the property we want to get at is that taking that pairwise vote is sufficient to figure out which alternative beats the other, okay? Well, if that property holds, then for these two profiles, the social preference should be the same, right? I mean, we're thinking about a pairwise vote between x and y, and we're saying here that the people who prefer x don't change in the two profiles, the people who prefer y don't change in the two profiles. So the outcome of the pairwise vote is the same in the two profiles. So the outcome, that is the winner, between those two will have to be the same. Okay, so the way I'll write that is that I'll just say the social preference between x and y is the same across those two profiles. Okay, and if you wanted to say that in a more rigorous way, kind of a logically precise way, what we would say is we would say that social preference for, we would say x beats y in the first profile if and only if it beats y in the second profile. Okay, so this is kind of the logical version of that. All right, independence for relevant alternatives, IAA. It's a mouthful to say, and it's kind of a mouthful to write down and a brainful to understand. But after a while, it becomes pretty intuitive. And what it's really saying is that, you know, to calculate the social preference, all you need is just a raise of hands, who prefers X and who prefers Y. Okay. Now, an interesting thing about these two properties here is that they're very, in a way, they're very unrestricted. We've really isolated specific properties of voting rules here. In particular, this doesn't say anything about unbiasedness with respect to individuals or alternatives, okay? Because, well, you can just kind of look. There's nothing here that says that a voting rule can't favor one alternative over another or favor one individual over another. Yeah, these are more general than you might really think. So let me next use a term I've kind of thrown around a little bit, but let me introduce it in a more explicit way here. I've talked about axiomatic analysis and axioms. An axiom is really just it's just a property of interest that's compelling, and these two properties that we've defined here in a formal way, those are axioms. Okay, so if you have wondered what an axiom is, you've just seen two axioms. There's the rationality axiom and there's the IIA axiom. Okay. Let's do one more axiom, and then I'll go through some examples to give you a better feel for how the axioms work. So actually, this will be the last axiom that I give, and I'm going to call it the Pareto axiom. Okay. What does it mean for a social preference function to satisfy this Pareto axiom? It means the following: for all profiles and all alternatives, if everyone prefers x to y, then x beats y according to the social preference function. Okay, that's all it is. And the way we would write that in a formal way is suppose that for all I, x, p, I, y, right? So this here in brackets just says every individual prefers x to y. Right? The Pareto axiom then would say that x has to beat y for the social preference function. Okay, this should seem like a very intuitive axiom. Certainly, from a normative perspective, any voting rule you would want to satisfy this. You know, this is not controversial. Okay, so we now have three axioms. Let's go back and think about these axioms, in particular IIA. Okay, let's go back to our board example from the previous installment, where we saw how the board scores were the board ranking was quite sensitive to information in the rankings. And so in that example, we had 9 individuals. There were only 4 rankings. So that was A, B, D, C, A, C, B, D, C, D, A, B, D, C, A, B. We had 2 people having each of the first 3 rankings, and 3 people had the last one. Okay, and then we calculated the Borda ranking, and that was A first, then C, D, and B. Okay. And then we said, well, let's move B down to the bottom of these rankings. And so we have then A, D, C, B, right? We're just moving that down. A, C, D, B, we move that to there. And these were the same. And we saw that, oh, just realized I'm using an M. This is the Borda. Okay. When we moved B down to the bottom of these first four rankings, we saw that obviously B was still bottom ranked, but it reversed the ranking of the other three alternatives. Okay. So I just want to point out that this is exactly the kind of thing that IIA says cannot happen. Okay. IIA says you can really only use information from a pairwise vote between two alternatives to see which one beats the other. Here we're using more than that. Let's actually be specific about this though and see how it violates IIA. Okay, so in the first, let's call the first profile our P profile, and the second one is our P prime profile. Okay, so in the first profile, let's notice we get a preference reversal here, right? In the first profile, A beats D. In the second profile, D beats A. Let me just put primes on those. Okay, now let's focus in on those two alternatives. And let's look at the set of people who prefer A to D in the first profile. Okay, so that's going to be formally it's this set. And if we look at this profile, that's going to be, well, these guys prefer A to D, so do these guys, but the other guys don't. So this is going to be the first four individuals, okay? Now let's go to the P prime profile, and let's ask who prefers A to D in the prime profile. And if we look at this, the first four guys prefer A, the other five guys prefer D. So again, this is the first four guys. All right. We can look at as well who prefers D to A, and it's just going to be the remaining people here because there's no indifferences in the rankings. So that's going to be 5, 6, 7, 8, 9, and here for the P prime profile, who prefers well, again, it's 5, 6, 7, 8, and 9. All right, and so what we see is that, right, so this right here is the outcome of the pairwise vote for the first profile, okay? Over here, we have the outcome of the pairwise vote for the P prime profile. And we see that these are the same, right? The same people prefer A to D. It's the first four guys. The same people prefer D to A. It's the last 5 guys. Okay? Right. IIA says that the social preference between the two alternatives has to be the same then in the two profiles because the outcome of the pairwise vote's the same. But obviously here we see a violation of that, right? The social preference does not stay the same in these two profiles. It reverses. So, so this is a violation of IIA. It shows that the Borda social preference function, the Borda preference function, does not satisfy this axiom. Majority rule does. You just go to the axiom and think about it, you can see that. So, all right, so we have 3 axioms. We've seen how they kind of reflect our informal discussion about the properties of majority voting and Borda, but now we're able to formalize them in a way that's general and systematic, and we can think about any kind of voting rule as a social preference function, and we can talk about whether that social preference function satisfies rationality or IIA or Pareto. Okay, so at this point, that's as far as I'm hoping to get for this installment. We've laid out, the social choice framework, and now we've formalized these axioms. In the next installment, I guess we'll just continue this, and we need to state Arrow's theorem, and then it is a very deep result. Once you're used to it, it's not that intricate, but the first time you see the proof, it has a tendency to blow people away. So we'll give it a try next time, and I guess that's it for now. I'll see you in the next one.